Hello friends, so welcome to a lecture series on non-linear programming. We were discussing dynamic programming, what dynamic programming are and what are their applications. In the last 1-2 lectures we have seen that how can we solve a problem on shortest path using dynamic programming, how can we solve allocation problem using dynamic programming and few more examples based on it. Now dynamic programming is also useful to solve some non-linear programming problems. How can we solve a non-linear programming problem? Let us see this in this lecture. Okay. Now take a first example, use dynamic programming to solve the following problem. It is a very simple problem. You see objective function is quadratic, that is minimum of x1 is square plus x2 square plus x3 square subject to x1 plus x2 plus x3 is equal to 15 and x1, x2, x3 all are non-negative. So how can we solve this simple problem, this simple quadratic problem in fact using dynamic approach, using dynamic programming approach. So let us see, let us try to solve this problem. So it is a simple problem minimizing z equal to x1 square plus x2 square plus x3 square subject to x1 plus x2 plus x3 equal to 50 and x1, x2, x3 all are non-negative. Okay. So we first mark out some state variables. Okay. How many variables we are having here? 3 variables we are having. So we will mark 3 state variables. So let us suppose k1, k2 and k3 are the state variables. So state variables. We mark a state variable say k3, k3 we take as x1 plus x2 plus x3 which is equals to 50, k2 we take as x1 plus x2 which is equals to from here from this expression it is equals to x3 minus k3 minus x3 and then k1 which is x1 which is equals to from here it is k2 minus x2. So these are the state variable which we let. Okay. Basically what we do, we first take this objective function my x1 square, okay, subject to k1 equal to x1. Then we take in the next stage we take these two objective functions. I mean x1 is x2 square plus whatever we obtain in the first previous stage, that is the dynamic approach. Okay. And the last stage, that is a stage 3, we take x3 square plus whatever we obtain the previous stage. Okay. So we start from stage say stage 1. So stage 1 is f1 k1. f1 k1 is the net output from stage 1. Okay. Net maximum value which we obtain from the stage 1. That is since a minimization problem, so it is minimization of, it involves only one objective x1 is square, so it is x1 is square subject to x1. So minimum of x1 is square when x1 equal to k1 is k1 is square only, so it is k1 is square. Okay. That is the first stage. Okay. In this approach we are moving in a forward direction. We first take this stage, then this stage and then the combined stage, stage 3. Okay. It is our choice whether we take backward approach, backward recursion or forward recursion. Here I am taking forward recursion. Now stage 2. In stage 2 we take f2 k2. What is f2 k2? It is minimum of x2 square. x2 square is this this objective function plus whatever you obtain the previous stage plus f1 k1 we are minimum over x2 and that is equals to minimum of x2 square plus it is f1 and what is k1? k1 is k2 minus x2, so it is k2 minus x2. Okay. K1 is K2 minus X2 and it is minimum of again minimum of x2 square plus, now f1 k1 is simply k1 is square. So f1 k2 minus x2 will be k2 minus x2 whole square. You simply replace k1 by k2 minus x2. So you simply replace k1 by k2 minus x2, so it will be k2 minus x2 whole square. Now we have to minimize this function, okay, and it is of only one variable x2. So we can use the derivative, concept of derivative. We simply differentiate this function, okay, and put it equal to 0. So derivative of this function, say it is gx2. Gx2 is x2 square plus k2 minus x2 whole square. So derivative of this function, put it equal to 0. So this implies 2x2 minus 2 k2 minus x2 equal to 0. So and this implies 2 cancels out. So this implies x2 will be k2 by 2. Okay, and what will be f2 k2? So f2 k2 will be equal to, you simply substitute x2 equals to k2 by 2 here. So it is k2 square by 4 plus k2 square by 4, which is k2 square by 2. So this up to this stage we have find out the minimum value of this function. Now stage 3, which is the last stage, stage 3 will be f3 k3, which is minimum over x3, okay, and x3 square plus whatever we obtained in the previous stage, that is f2 k2, and k2 is nothing but k3 minus x3. So it is plus f2 of k3 minus x3, because this objective function, I mean this function x3 square plus whatever we obtained in the previous stage, and previous stage is f2 k2 and k2 is k3 minus x3. So f2 of k3 minus x3, and this further equals to minimum of x3 square plus, now f2 k2 is k2 square by 2. So that means, so f2 of k3 minus x3, you simply replace k2 by k3 minus x3. So this will be equal to k3 minus x3 whole square by 2. Now again it's a one variable problem. So we simply differentiate it with respect to x3 and find out the minimum value of this function. So we simply differentiate this with respect to x3. So it is 2x3 plus minus 2 k3 minus x3 upon 2 equal to 0. So 2 cancels out, and this implies x3 will be equals to k3 by 3. And what will be f3 k3? For f3 k3 you simply substitute x3 equals to k3 by 3 over here. So what we obtain? We obtain k3 square by 9 plus when you substitute k3 equals to x3 equals to k3 by 3. So it is k3 minus k3 by 3 whole square into upon 2. So that we can easily solve. It is f3 k3 will be equals to k3 square by 9 plus, it is 4 by 9 k3 square by 2, that is it is k3 square by 3. Okay. Now what is k3? So this is the maximum value of the entire objective function z, minimum value of this objective function z. Okay. Now what is k3? k3 is 15. Okay. So this implies f3 k3 will be 15 square upon 3, which is 45. So, this is the maximum value of the objective function, sorry, minimum value of the objective function. Now, at which points, for what are the values of x1 and x2, x3? So x3 is k3 by 3, x3 is k3 by 3 and k3 is 15, so it is 5. Okay. Now, x3 is 5. Now, k2 is k3 minus x3. Okay. K2 is k3 minus x3. Okay. So, k3 it is 15 minus 5, that is 10. So, what will be x2? x2 is k2 upon 2. Okay. So, it is k2 upon 2, 10 upon 2, that is 5. So, x3 is 5, x2 is 5. Now, k1 is k2 minus x2, that is 10 minus 5 equal to 5, and it is at x1 equal to k1. So, x1 equals to k1, so that means equals to 5. So, that means minimum is obtained when all x1, x2, x3 are equal and equal to 5. So, that is how it is a simple illustration that how can we solve some non-linear optimization problems using dynamic programming approach. We simply first define some state variables k1, k2, k3 depending on the number of variables involved in the problem, okay, and then we find out the stages, stage 1, stage 2 and so on, depending on the number of variables. Okay. Suppose there are n variables involved in the problem, so there will be n stages and the final stage will give the optimal solution of the problem. Okay. So, this PPT shows the solution also. Now, second example, again a simple example, it is minimum of f is equals to y1 cube plus y2 cube plus y3 cube subject to y1 into y2 into y3 is equals to 8 and y1 greater than 0, strictly greater than 0 for all I 1, 2, 3. Of course, y1 can't be 0 because if y1 equal to 0, so the product can't be equal to 8. If any one of the y, either y1, y2 or y3 becomes 0, so the product cannot be equal to 8 and we need the product equal to 8. So, yi's can't be 0. So, we are assuming y is strictly greater than 0 over here. Now, again it is a 3 variable problem. So, we defined state variables k1, k2 and k3. So, first we defined k3. K3 is simply y1. Here instead of addition constraint, we are having constraint in the multiplicative form y1, y2 and y3, multiplication involved. So, we take as first state variable k3 as y1 into y2 into y3 which is equals to 8. K2 we take as y1 into y2, only these two variables, okay, which is equal to, from the first condition, y1 into y2 is k3 divided by y3, this value, okay, and k1 is only this y1 which is equals to, from this condition, again from the second condition, y1 is k2 upon y2, So, in this way we have defined 3 state variables k3, k2 and k1. Okay. Now, the stage 1, again the stage 1 we take minimum of the first component of the objective function, that is y1 cube. In the second stage we take y2 cube plus whatever we obtain the previous stage, that is stage 1. Okay, it's an addition here. If it is the objective function also multiplication is involved, then we multiply, okay, in the stages. So, in the first stage it is f1 k1 which is equals to minimum of y1 cube is here and y1 is equals to k1. So, minimum is obtained only at k1. So, it is k1 cube. Now, in the second stage here the second component is y2 cube, okay, and whatever obtained from the first stage, that is f1 k1, and k1 is, from here k1 is equal to k2 upon y2. So, in the next stage, okay, in the next stage it is y2 cube plus f1 of k1 is k2 upon y2, okay, and f1 upon k1, yeah, from here f1 upon f1 k1 is equals to k1 cube. So, here k2 upon y2, f1 of k2 upon y2 is equals to k2 upon y2 whole cube. Now, it is again a single variable function of y2, you differentiate it with respect to y2, put it equal to 0, then you can get the stationary point for which this value is minimum. Okay. So, you differentiate with respect to x y2, put it equal to 0, we get y2 is equal to under root of k2. Ignore the negative value because y1 y2 are strictly greater than 0. Okay. So, f2 k2, from here we obtained f2 k2 is equals to, when you substitute y2 over here in this expression, we obtained f2 k2 is equals to 2 times k2 whole raised to power 3 upon 2. Now, in the next stage again we take y3 cube, minimum of y3 cube plus whatever we obtained the previous stage, that is f2 k2, and f2 k2, and if you see here f2 k2, if you see here, sorry, if you see k2 is equals to k3 upon y3. So, you simply replace k2 by k3 upon y3, and as f2 k2 is 2 times k2 whole raised to power 3 by 2. So, you simply replace 2 into k3 upon y3 whole raised to power 3 by 2. Again it is a single variable function of k3 of y3, you differentiate it, put it equal to 0, find out the stationary point which will give the minimum value of this objective function. So, in this way we get y3 is equals to k3 whole raised to power 1 by 3 and the minimum value of this function. Now, we know that k3 is equals to 8. So, substitute k3 equal to 8 here, we get y2 equal to 2, as k2 equals to y3 upon k3 and y3 is 8 upon 2, that is 4. So, this implies y2 is 2. Why y2 is 2? Because y2 is under root k2. Okay. You substitute 4 here, so y2 is 2. And similarly, k1 is k2 upon y2, so 4 upon 2 is 2 and y1 is 2, because k1 equal to x, y1 equals to k1. So, in this way that means the optimal value of this objective function is obtained at when y1 is 2, y2 is 2 and y3 is 2. Okay. Now, let us come back to this problem. Now, let us come to this problem using dynamic programming, how to find a point in the first quadrant nearest to the origin on the straight line this. So, let us try to find out solution of this problem. So, what is the problem? Problem is to find out the point which lie in the first quadrant and nearest to the straight line this. So, what is a straight line? A straight line is 2x plus 3y equal to 6, that is 1 2 3 and 1 2. So, this is a straight line, okay. It is 2x plus 3y equal to 6. So, we have to find out a point on this straight line which is nearest to the origin, okay. So, of course, that point will be the foot of perpendicular from origin. If you draw a foot of perpendicular from this point on this line, so this foot of perpendicular will be a point on this line which is a shorter distance from origin. So, we can easily find out this point P, which is the shortest distance from origin on this line using coordinate geometry also. We can simply find out the equation of this straight line, okay, and then the point of intersection of this straight line with this straight line gives the point P. But the same problem can also be solved using dynamic programming. So, how can we solve using dynamic programming? Let us see. So, suppose this point is say x comma y, which you have to find out. Okay. So, distance from the origin will be, distance of origin from this point to this point is under root x square plus y square. Distance, this distance OP, this distance OP is under root x minus 0 whole square plus y minus 0 whole square. So, this is to minimize, and xy must lie on this line. So, subject to this condition, and we want point is in point should be in the first quadrant, that means xy both should be non-negative. Okay. So, we have to minimize this is same as minimization of this is same as minimization of square of this value. Minimization of this quantity is same as minimization of the inside the value inside the under root. So, we simply minimize this expression. Okay. So, what is the problem? Problem is minimization of z, which is x square plus y square, and subject to the point must lie on the line, that is 2x plus 3y must be equal to 6 and xy must be non-negative, because point should lies in the first quadrant. Okay. So, this is the problem, this is the formulation of the problem. Now, how can we solve this problem using dynamic programming? Again, we first define state variables. Okay. So, state variables are first is k2, only two variables are here x and y. So, we will be having we will be having two stages k2 and k1. Okay. So, k2 will be 2x plus 3y, which is equals to 6, and k1 will be equals to 2x. Okay, this 2x, and this 2x is equals to k2 minus 3y. Okay, from this expression k2 minus 3. Now, we start from stage 1. Stage 1 is f1 k1. f1 k1 is minimum of the first value, that is x square, and this is over 2x equals to k1, I mean over x1 over x. And what is x? X is k1 by 2. Okay. So, minimum will be k1 by 2 whole square, which is k1 square by 4. Now, come to next stage or the last stage of this problem, because it is only two variable problem, a simple illustration to solve such type of problem using dynamic programming approach. Okay. So, it is f2 k2, which is minimum of y square plus whatever we obtained in the previous stage, that is f1 k1, and k1 is k2 minus 3y. So, it is k2 minus 3y. Okay. And it is further equals to minimum of y square plus, now f1 k1 is k1 square by 4. So, f1 of this quantity will be this square by 4, that is k2 minus 3y upon whole square upon 4. Okay. Now, again it is a minimum over y. Okay, minimum over y. Now, it is a single variable function of y only. You again differentiate with respect to y and put it equal to 0 to find out the minimum value of y, minimum value of this objective function, sorry. Okay. So, you differentiate it with respect to y. So, that will give, so suppose it is gy, where gy is y square plus k2 minus 3y whole square by 4, derivative of y put it equal to 0. So, this implies 2y and minus it is 6 times k2 minus 3y upon 4 and put it equal to 0. Okay. So, that will be that will be 2y, which is equals to 3 upon 2 times k2 minus 3y. This implies 4y is equals to 3k2 minus 9y, and it is 13y is equals to 3k2, and y is equals to 3k2 upon 13. Okay, this is y. If you take the second derivative of this quantity, so second derivative will be negative. You can check. Okay. Now why is this? So what will be now k2 is 6. Okay, k2 is 6. So this implies y is equals to 3 into 6 by 13, which is 18 upon 13. And now k1 is k2 minus 3y. So it is 6 minus 3 into y. 3 into y is 18 upon 3. Okay. Now that it is equals to that is 78 minus 54 upon 13. Okay, and that is equals to 24 upon 13. So that will be k1. And what will be x? X is k1 upon 2. So x will be k1 upon 2, that is 12 upon 13. So the optimal solution is 12 upon 13 and 18 upon 13. So this is the point which is at the nearest distance from origin and on the straight line this. So that is how we can solve this type of problem also using dynamic programming. So these are some simple illustrations of dynamic programming, that how can we solve few non-linear programming problem using dynamic programming approach. So in the next lecture we will see how can we solve some non-linear problems using such techniques. Okay. So that will be our next lecture. So thank you very much.